Okay, so I've been working for a while on, quantum error correction, finding good codes, and then I want to, go to the next step, which is fault tolerance. And for me, it looks, this field of fault tolerance, it looks very messy. So I'm trying to understand kind of the basic questions. So in general, the goal, what it is you want to perform a computation. So the way you do that, you encode your data in some quantum error correcting code. And then really the challenge is to, perform, computation on that data, which is protected in the quantum code. So this begs the question, how do you find encodings, codes, for which, if you want to implement a logical gate, then you get a nice physical implementation of that. And by nice, I mean, it can mean different things. It can mean, if you have, qubit codes, can mean that the gate is implemented with a low-level, low-depth circuit, like a transversal gate. If you have a bosonic code, then maybe the kind of operations that you want to do is like linear optics, so Gaussian operations, like we mentioned. More generally, maybe you want some kind of continuous representation of the gates onto your physical system. So I think there's kind of a very nice formal problem that you can study, and this is this one, and this is basically the thing that I want to study in this talk. So the setup is as follows. So you have a qubit, which is the system that you want to protect. Okay, you want to protect a single qubit, say. And then you want to perform some gates. You want to do some computation on this system. And the way you do that is by where is the okay, so what you want to do, you want to apply some gates on your system. So maybe you want a logical group that you can implement, which will be a subgroup of SUD if you have a qubit. So maybe this group is like the single qubit Clifford group. Okay, so that's the setup. You have this qubit, and you want to implement some gates. So this is at the logical level. At the physical level in the lab, what do you have? So you have a physical space. It can be an n-qubit space. It can be a Fock space if you have a bosonic encoding. It can be whatever you want. And then what you really want is, for this group of gates that you want to implement, you want to have a nice physical representation. So basically what you want is that for any gate in that group, you want, a physical operation that acts on this physical space and that will implement the gate. So again, this can be Gaussian unitaries, this can be transversal gates. So transversal gate is just this. Basically, you apply the same gate on the n qubits if you have an n qubit encoding. And the question that I want to ask is that, can you design encodings, quantum error correcting codes, for which all the gates in that group, they are implemented with that physical representation? Okay, well, so what does that mean? So you have this encoding from CD to your Hilbert space, and what you want is that if you act on the encoding of some psi, and you act with this rho of G, so the representation of the element G of the group, then what you get is the encoding of G of psi. Okay, so this is the question I want to study. And this was studied, I think, kind of the first papers I saw kind of study these kind of questions was by Jonathan Gross for spin encodings. But I want to ask the question more generally, okay? Okay, so there will be some limitations. You cannot do whatever you want like this. And one well-known limitation is the Eastin-Neal theorem. And it tells you that if you focus on transversal implementations, so if your physical representation is a transversal implementation, so you implement G by applying G on every qubit, then you cannot get a universal gate set in that way if you also want your encoding to correct or to detect errors. And a kind of a baby version of this is that you cannot take your group, the group of gates that you consider to be infinite, and the representation to be continuous. If you could do that, what you could do, you could pick two arbitrary close elements of this group, T and G prime, and then if rho is continuous and everything, you're an SUD, so everything is compact, then the two physical representations, they will be very close, better than what you can achieve with experimental precision. And then it means that if you apply these two gates, one of these two gates, you cannot really distinguish them in the lab, and you will prepare two encoded states that you cannot really prepare with arbitrary precision. You don't know which one you get, and so this is incompatible with fault tolerance. Okay, so there are limitations. You cannot take G to be infinite and rho to be too nice. So there are ways around this, and this is, you can do approximate quantum error correction, but this is not something I want to look at today. Okay, so in that paper with a student with Ray Denis, last year what we showed is that there's a very simple recipe to do that. So again, the setup is you have this group in SUD, you have some physical representation in your physical system, and the goal is to find an encoding that satisfies this thing. And turns out there's a recipe to produce all the encodings that do that. And basically, so there's the formula here. So what you should do, you should pick some arbitrary state in CD, an arbitrary physical state in your physical space. And then you can write down an explicit encoding of this form. So basically, the encoding of psi, for any psi, it will be a superposition of this kind of elements. So you have this arbitrary physical state phi, and you apply a rho of G to this phi, and then you have some amplitudes that are given by these coefficients. Okay, so you can always do that. So for any choice of omega and phi, you get an encoding that has this kind of covariance property. So you can do that, for instance, with bosonic codes. So for bosonic codes, maybe the physical state that you want to start with is a multimode coherent state. Kind of nice state you can do in the lab easily. Maybe the representation that you want to look at is Gaussian passive unitaries. So basically, if you have for a qubit, if you have a two-mode coherent set alpha, what you can do is you can define Gaussian unitaries that will act on this alpha by just doing the rotation G in phase space. So this is like a rotated coherent state. And then if you do that, what you get is that you have an encoding where the encoded states, they're just superpositions of coherent states. Okay, and so you can do that. This kind of generalizes something called quantum spherical codes that were introduced last year. But the difference here is that now these things, by construction, they have nice gate sets. So this construction may look weird, but in fact, if you apply this to kind of nice groups, natural groups, and taking natural, physical states, you can recover the kind of the usual suspects. You can recover the GKP encoding if you take the Weyl-Eisenberg group and displacements for your representation. You can get cat qubits if you take the cyclic group and phase shift. So you can really recover kind of the standard bosonic codes. So let me say just a few words about representation theory. So kind of the idea behind this is that for any physical representation, you can always write it like this. So you can always write or decompose any representation as a direct sum of irreducible representations. So there's some kind of unitary that is called the intertwiner that tells you how to change the basis between these two representations. And then this lambda is just an irreducible representation of the group. And this M lambda is the multiplicity space associated with the irreducible representation. Okay, so basically any representation, you can write it like this. And if you do that, you can rewrite the encoding that I was mentioning before in that way. So basically, kind of the encoding map or the encoding unitary is just the unitary that does this intertwining between the representation and the direct sum of irreps. Okay, so it means that you can rewrite this encoding as some unitary applying on psi, and there's an additional state that you can choose arbitrarily, and this state phi, it lives in the multiplicity space associated with the irreps that you're looking at. Okay, so this is a second way to kind of write any encoding that will have this covariance property that I was looking for. So basically, U is given to you, is just fixed basically by the choice of the representation, and then you have this freedom to choose any state phi in the multiplicity space. And if you do that, one way to understand the kind of the construction is that the information is encoded into an irreducible representation of the group. Right? So this works for Bosonic codes, but this works more generally. So this works for qubit codes, where you encode one logical system into n physical systems, so 1 qubit into n qubits if you want. So you can focus, for instance, on transversal gates. So this also has been looked at in quite some details by Kubishta and Teixeira. And so you can play with this, and you can try to, kind of recover the standard qubit codes. So if you look for, a 5-qubit code where you consider the group G to be it's called the binary tetrahedral group. So it's just the group generated by Z and Hadamard. So it's a group of order 24. And if you choose kind of this representation of the group, and the physical representation is just the tensor product representation, so you apply the same gate on the 5 qubits. Then you just do the construction, and any encoding that will satisfy this, it will be of this form. And again, the only choice that you have is this state phi that lives in the multiplicity space of this C-rep. And this multiplicity space has dimension 6. Okay, so any choice that you make, you will get a code that has this covariance. But now the question, of course, when you do quantum error correction, you want the code to protect information, to correct errors. So that's the question. So can you choose a state phi that will do that? So in principle, you can just optimize over phi. You can just try to satisfy all the nil-Laflamme conditions for single qubit errors. If you try to do that on paper, it's not so easy. But there's an algorithm that kind of does that. In principle, it's not so too complicated. And that's what I did is I just asked ChatGPT to try to write a Python script that does that. It looks for all these phi states and tries to see whether you can satisfy all the nil-Laflamme conditions. So I let it do that, and I exchanged for a couple of hours because it gives you a script that doesn't compile, and you start again. It doesn't find anything, and then you say, okay, let maybe do this way and do this way. And then after 2 hours, you recovered a stabilizer code that was isomorphic to the 513 qubit code. Okay, so this works well. Then you can also try to do that for the STIN code. You can try to recover the STIN code. Turns out that the STIN code has transversal single qubit Clifford gates. So if you take this group now, the binary octahedral group, so it's generated by S and Hadamard, you can play the same game. And again, you can ask that the physical representation of the gate is just the tensor product representation. And if you do that, that in principle you can recover the standard STIN code. Again, if you choose the right state in the multiplicity space. But here the problem is a bit more complicated because the multiplicity space has dimension 15. So it's not really clear whether there's a systematic way of, if you know the code in advance, you can of course recover it. But if you don't know the code in advance, it's not so clear how to pick the state in the multiplicity space so that you get the nice codes with good error correction properties. So again, I tried to ask ChatGPT. So he found some codes, but they were not stabilizer codes. So they are not, the standard STIN code. It's a question that I don't quite know how to answer at the moment. How do you, find a way to systematically pick the right state phi in the multiplicity space so that the code that you get at the end has good error correction properties? So there are approaches to do that, but yeah, it's not. I don't think this question is well understood at the moment. Okay, and now I want to say a few words about these Fourier codes. So I want to go back to basically the Bosonic setting. And I want, sorry. I want to look at, kind of a nice example. So the encoding, I said, is the unitary that does this intertwining between the physical representation and the decomposition into a sum of E-reps. And one case where this kind of encoding is nice is when the physical representation acts like the left regular representation. So what it means is that if the physical states, they are indexed by the group elements like this, psi g for any g in the group, the left regular representation will act in this way. So for any group elements g and h, if you apply a rho of g to some state psi h, what you get is a new state psi gh. Okay, so you multiply on the left by g. And if you do that, the intertwiner just becomes the Fourier transform. So your encoding map in your code will be the Fourier transform associated with the group G. So it kind of looks nice. So you can do that for Bosonic codes. So if you have a Bosonic encoding and you take rho to be passive Gaussian operations, as we discussed before, so if you start with some state alpha, you apply rho of G, it moves to some other coherent state G alpha. And there's a way, so all these G alphas, if you have coherent states, they will be linearly independent. So you can find a way to find an orthonormal basis indexed by the group elements, psi G. And if you do that, then your encoding, you just apply this inverse Fourier transform, and you get an encoding of a code. Okay, and this encoding, now it encodes two qubits or two qubits, one corresponding to the logical qubit in the logical, like in the space of the E-rep, and one corresponding to a qubit in the multiplicity space of the E-rep. So now you get a code that encodes, two systems, a logical qubit and a multiplicity qubit. And then you can do that, and you can do that for a simple group, which is just the real Pauli group, okay? So generated by X and Z. And if you do that, you get something quite nice. You get a nice code. It's a Bosonic code on two modes. So if you pick this choice of initial state alpha, so alpha I alpha for alpha equal square root of pi over 2, you get these 4 encoded states because you have 2 qubits now that are encoded, which are products of cat states. Okay, so 1 alpha is just alpha minus alpha, so just a cat state, odd cat state, and this is an even cat state. So if you do that, by construction, because the group that you started with is the Pauli group, all the Pauli logical operations, they're easy to do. You can just do it with Gaussian passive unitaries. So it's just a swap physical gate for doing logical X, dephasing by pi for doing a logical Z. Turns out that the phase gates, they're also kind of nice. They're kind of the standard things for Bosonic codes. So you can do them with Kerr interactions, so polynomials of order 4 in the quadrature operators. You can also do these gates with quantum Zeno effect. So this is kind of standard. But you don't yet get a universal gate set. If you want a universal gate set, you also need to do Hadamard. Okay, and Hadamard is a little bit more tricky. It's also kind of interesting. So in principle, if you just do a row of H, it shouldn't be like a logical operation because H, the Hadamard gate is not in the group that I'm considering. The group is just, the Pauli group. So it's not a logical operation, but it's quite close. If you do that, what you do, in fact, what happens is that you're implementing Hadamard on both qubits, both the logical and the multiplicity qubit, and at the same time, you have a rotation of your constellation of coherent states. So you have some kind of code deformation. Okay, so you are really applying this gate with some kind of code deformation. And this kind of thing, it happens for any gate that is in the normalizer of the group. Okay. But then I was a bit stuck because if you have only this kind of gate, it's not clear whether this gives you like a universal gate set. And then I was stuck. I was chatting with ChatGPT again. And I was saying, okay, I have all these gates. Do I get, is there a way to see that I have a universal gate set? I said, yeah, because you can use this kind of trick. You can use SHSHS equals Adam out. And if you use that, and you apply this with this kind of gate, HL and HM, what happens is that you really, the HL, it will go through that. Using this formula, you will get HL, and HM, they will just cancel out. So ChatGPT told me that, but Ulysse, the other day, told me that this was already in a paper by Aronson and Baynes on correlation. So probably ChatGPT knows about this paper, and he knew this answer. Yeah, so I think this kind of Fourier code is not too bad. So this is probably more for experts. There are ways to kind of stabilize the code words that are not too crazy. It looks like other codes, Bosonic codes that people have looked at, like a four-legged cat, and two repetition cat, and pair cat codes. So these are codes that people have studied in literature. So for these two-mode Fourier codes, kind of the things that you need to implement them in the lab, they look kind of reasonable. And okay, so I want to conclude now. So basically, the whole point of this talk is really to try to find a general formalism to design codes for which, some logical gates, they come with easy to implement physical gates. So if you do that, with Bosonic codes, you recover kind of nicely GKP CAD encodings with, without any fine tuning. These codes come up directly. If you want to do that with qubit codes, it's less clear. The code that I presented at the end, these Fourier codes, I think they're kind of nice. The idea of encoding the Fourier transform looks kind of, kind of natural. I haven't seen many constructions like this, but probably there's something to dig a little bit in that direction. And there are many open questions. One of the main ones is that, all this, this approach gives you many codes that have the right covariance properties. But then how do you choose within all these possible codes which ones have the good parameters, which ones are good for, really correcting errors? And it's not so clear. Also, something which is not clear at the moment is that, if you apply this, the group G that you should start with should be finite. And then it cannot be universal. It's not a universal gate set, so you need to complete to find new ways to encode the remaining gates to get a universal gate set. And at the moment, it's still very ad hoc. Is there like a general approach to do that more naturally? I don't know. And with that, I would like to thank you.
Any questions?
Thanks. So in particular about your first question, I was wondering whether there is a classical analog, again, of the, sorry for asking the same question.
Yeah.
Like, right, can you, transversal classical code also makes sense. Can you somehow, I don't know, look at permutation representations just to get a feeling for that?
Yeah, it's a good question. I haven't thought of that. Can you do that? If you do, transversal implementation in the classical case, there's one operation that you can do on a single bit, which is just bit flip, no? So if you want to do something, it's just you will just
like bigger fields, no?
What?
You can have bigger fields, no, than FQ.
Yeah, over FQ. Yeah. But still, I think if you do that in the classical case, you will apply the same operation to everyone. So probably you have something that looks, the old one or the old I code word should be a code word of the of your code. So I think it will restrict the encodings quite a bit. No, but it's a good question. Yeah, thanks.
Any other questions? If not, let's thank Anthony again.